Hello, welcome to all. In the previous lecture, we covered Gauss Law and its applications. First application we covered in the previous lecture is infinite state of charge, and the second application we covered only partly is charged cylinder. In the yesterday's class, we found the electric field for outside points of the charged cylinder. Okay, we got the expression for E as rho r square by 2 pi epsilon naught r. What is the case we discussed yesterday? R is greater than R. Okay, this applies for the points outside of the charged cylinder. Okay, what is the meaning of this formula we derived in the previous lecture? Okay, here E is a function of R. Why? Because on the RHS you have R, that too in the denominator. So as you increase the value of R, E value goes on decreasing. Where it applies? It applies to the points outside of the surface of the original cylinder. So as you move away from the surface of the cylinder, then the field due to the charge on the charged cylinder goes on decreasing. Okay, this is what the physical meaning of this expression. Okay, right. This is about what we studied in the yesterday's class. Now I will show you the plan of today's class. In today's class, we are going to complete this infinite cylinder problem, and apart from that, we are also going to study the applications of field of parallel planes and derivation of Coulomb's law from the Gauss law of electrostatics. That means here our problem under consideration is a point charge. Okay, right. Now let us go for the first of these things, infinite cylinder, which we are already started yesterday and solved half of the problem. Okay, now we are going to find the electric field inside the circular cylinder. Okay, for that what we have to do? We have to draw the Gaussian cylinder inside of the original cylinder. Okay, right. Okay, now here I am erasing this Gaussian cylinder. Now I am going to draw it so that it passes through the points inside the circular cylinder. See, I am reducing the lateral dimensions of our earlier Gauss surface. Say, now your point P is shifted to here. Say, let us say this is P point. Of course, you may put P here also. You may call this P prime. So now our Gaussian surface must pass through these points laying inside the circular cylinder. So our option is again cylindrical Gaussian surface which passes through these 2 points, or this one point P. So now I am pushing our Gaussian cylinder into the original cylinder. This is our Gaussian surface. It is completely laying inside the original cylinder. Okay, now let us go for the second case. is for inside points. That means field inside of the circular cylinder. So what is the mathematical form of this statement? Now you see, this is a capital R, this is small r. Here small r is less than capital R. Then only your point will stay inside of the solid cylinder. Okay, this is the restating in mathematical form. Right. Now, according to the Gauss law, you will write this is integral E dot ds is equal to q by epsilon naught. Simply I am writing the Gauss law as it is. Okay, now we have to modify this according to our problem. We have to apply this for this Gaussian surface which is laying inside the original cylinder. Okay, right. Now how much charge is there inside this imaginary surface? How much charge is there? See, now it is the problem is similar to the uniformly charged sphere. Why? Because you need only the charge which is inside the imaginary surface, that is Gaussian surface. Charge is filled in this entire cylinder, but now your imaginary cylinder is smaller than the original cylinder, so it is leaving some of the charge which is laying inside the original cylinder. We only need the charge present inside the portion of the Gaussian surface. Okay. Anywhere inside the original cylinder, per unit volume you are having how much charge rho. So here for the volume of this small cylinder, how much charge you have? Yeah, this is integral. Charge is integral rho dV. Okay, by epsilon naught. Okay, rho dV. But here this integral rho dV refers to this imaginary cylinder. Okay. Now, as rho is a constant, yeah, you may write that outside of the integral symbol. Okay. Yeah. Now, what is your integral dV? Total volume here. What is your total charge here? Charge laying inside this small cylinder. So now this volume, integral dV, is the total volume of this imaginary cylinder with radius r and length. Length is same as before, it is L. Okay, so now what will be the rho dV? Total, okay, now I am writing here. Yeah, integral E ds is equal to rho. What is the total volume of a Gaussian cylinder? Pi. What is your over here now? Small r. R square. H means height means L. Pi r square L. Here you have to be very careful whether you have to take small or capital or here. Okay. Right. This thing by epsilon naught. Okay. Now we almost completed the calculation of RHS. Now we have to go for the LHS. What will be the LHS for this Gaussian cylinder? Okay. Yeah, what is EDS now? You simply write EDS cos theta. But how many surfaces are there here? Again, here also you have three surfaces: top surface, bottom surface, and lateral surface. Okay, if it is your point, here you have to take an infinitesimal area. See, this is a ds. This ds will point this side. Okay. Now, for this surface, your E and your ds are parallel. So, the integral referring to this lateral surface will be non-zero, as in the previous case. Next, the integrals referring to top and bottom portions will be zero. Why? See, ds is directed perpendicular to E. That's why here you have ED as cos 90 means that is 0. So now here you have only one non-zero integral. So after expansion you may write that E ds cos 0 is equal to, remaining two integrals are 0. Okay, rho pi r square L by epsilon naught. Since cos 0 is 1, this is simply integral E ds is equal to rho pi r square L by epsilon naught. Okay, again E is constant on this lateral surface, so you may take E outside. Okay, so after the integral symbol you have only integral ds. Okay, on this side you have 4 pi r square L by epsilon naught. Okay, now what is this integral ds total area? Total area of what? Gaussian surface. That too, which part? Lateral part. So total surface area of this cylinder with the radius r and height L is pi r L is equal to rho pi r square L by epsilon naught. Okay, it is area, that's why you are having 2 dimensions for length. Here you have 2 plus 1, 3 dimensions for length. Okay, now you simply simplify this expression. L is cancelled, L is cancelled. Next 1 r is cancelled. Here you are left with 1 r, pi are cancelled. Next you are only left with E is equal to rho r, okay, by rho r by 2 epsilon naught. 2 epsilon naught. Okay, rho r by 2 epsilon naught. So what is your expression now? I am writing here. You see, E is equal to rho r by 2 epsilon naught. Okay, this is a final expression for the electric field intensity inside the charged cylinder. See, what is the difference between our previous formula and this formula? Where it is applicable, case B means for inside points. Here, what is the condition? R is less than R. So this formula is applicable in this case. That means for inside points of the charged cylinder. Okay. Now, what is the meaning of this expression? Physical meaning. Here it is also a function of R. Okay, R. See, this R never exceeds the base radius of the original cylinder. So it refers to the inside points. So as you move from the axis of the cylinder to the surface of the cylinder, what happens to its field intensity? As you move near to the surface, electric field intensity increases. Why? E is proportional to R. That is what the difference between expression for Gauss law for inside points and outside points. For inside points, as you move away from the axis of the cylinder, electric field intensity increases. It reaches maximum at the surface of the cylinder. As you move away from the surface, then what happens? It gradually falls as R. Okay. Here, in both cases, the change is either proportionality or inversely proportional to small r only, not r square. Okay. You see in this slide, okay, now here you can see in this slide, see for R is greater than R. That means for outside points, E is inversely proportional to R. For inside points, that is when R is less than R, you have E is proportional to small r. E is proportional to small r. Okay. Yeah. If you try to draw a plot between E and R, then what will be the shape of that plot? Okay. Yeah. Okay. Yeah. Here, this is the y-axis, this is x-axis. Okay, on this axis we are taking R, and on this axis we are taking E, electric field. Okay, say this as a center of some point, center point on the cylinder. Okay, this point is on the axis of the cylinder. Here this is R, this point is R is equal to 0. It shows the axis. So as you are moving away from the axis towards the surface of the cylinder, then what happens? Its value, E value, goes on increasing. Okay, E is proportional to R. Okay, right. Next, as you move away from the surface, you are already reached the surface, and now you are moving away from the surface. Okay. Okay, this is say this is cylinder, no? Okay, up to this point you have this line. So when you cross this border, then what happens? Your graph will be like this. What is this point? What is the coordinate here? R value is equal to R here. Okay, so as you move up to the surface, electric field intensity increases. As you move away from the surface, electric field intensity decreases. Okay, we are saying this, we are coming to this conclusion by the use of Gauss law for this particular problem. So the expressions derived from the Gauss law are saying that up to this point, electric field varies like this. So after this point, electric field varies like this. Okay. Yeah, this is about the application of Gauss law of electrostatics to the charged cylinder. Okay. Yeah, next let us go for the parallel plate problem. Yeah, now you can see the parallel plates here. Here we want to apply the Gauss law for this parallel plate problem. That means here you may try to find the electric field in between the plates, or on the side of a positive plate, on the other side of the negative plate. Okay. okay, adjacent to the negative plate outside, adjacent to the positive plate outside, this side, okay. Yeah, you see it is appearing like a parallel plate capacitor. Yeah, here the field is almost uniform as long as you take the plates of very large dimensions, okay, and the distance between these two plates is very small compared to the dimensions of those two plates, okay. It's a known problem. Yeah, now where are the field lines? Field lines are between the plates. There are no field lines outside the plates, so you have the electric field in between those two plates. We have to prove that with the help of Gauss law. If at all there is field, what is the magnitude of that field? So far we applied the Gauss law for single plate infinite sheet of charge. Here instead of that we are having two plates. You know the field very near to the infinite charge sheet, that is sigma by 2 epsilon naught. But why you are not having the field here? Why you are not having the field here or here? You are only having the field here. Yeah, here you have to draw the field lines individually for each plate. Now I am drawing here. See, this is this is one plate. Yeah, this is another plate. Okay, actually these two plates are very near to each other, but for understanding purpose I am drawing them apart. Okay, say this is a positive plate. Okay, say this is a negative plate. See, here you may directly apply the Gauss law for this plate and this plate. Why? Because we already applied those Gauss law for individual plates, infinite sheet of charge. We need not to rederive it by using the Gauss law. Just I will make use of the result for each plate. Okay. Right. Now, first of all, let us draw the field lines. As it is a positive plate, first consider only one plate, plate A. This is plate B. Okay, let us consider only one plate here. This is plate A. This is plate B. Okay, here let us draw the field lines for this plate. As it is a positive plate, field lines emerge out from this plate. Irrespective of the second plate, its field lines will go like this. Okay, now on this side also you have field lines like this for the plate A. Okay, due to the positive charge on plate A. Next, let us forget about plate A and let us go for the plate B. Okay, this is a plate B. It is a negative plate, that means negative charge is stored on this place. Okay, let us imagine that surface charge density is same for both plates except the sign. Okay, yeah. Now let us draw the field lines for plate B. It is a negative plate, that's why field lines always enter into the plate. Okay. Yeah, field lines enter into the plate. Field lines enter into the plate. Okay. Like this. Of course, irrespective of this plate, they enter into the negative plate. Okay. Here, say this is plate A electric field. EA, this as a EB. Yeah, this is the electric field of plate A, this is electric field of plate B. So now here we have to apply the superposition principle for the fields. Okay, say E, this is again okay, this is upper arrows referring to the plate A, lower arrows are referring to the field B. Okay, now in order to find the total electric field due to these two fields prevailing in that area, that means in all the three partitions 1, 2 and 3. Okay, now what is EA, what is EB? Both are same. Either EA, you know that this we already evaluated, sigma by 2 epsilon naught, as EB also magnitude. I am talking about the magnitude. EA, this is equal to EB. Okay, so EA and EB are same in magnitude. That magnitude value is 2 by epsilon naught. Okay, yeah. Now apply the superposition principle separately in each and every region. Okay, in this region, E is equal to EA plus AB. Okay, here also E is equal to, say this is E1, say this is E2, yeah, EA plus EB. Okay, here also E3 is equal to EA plus EB. These are all the vectors. Okay, now you come to know the total electric field in region 1, in region 2 and in region 3. Okay, now let us go for the first one, field in region 1. See, how do you write this? EA, vector addition is there. EA is how much in magnitude? It is sigma by 2 epsilon naught. EB is also how much? Sigma by 2 epsilon naught. But it is pointing in this direction. It is pointing in this direction. So here you have to write the negative sign. Okay, if it is positive, it is negative. Okay, sigma by 2 epsilon. This is equal to 0. Okay. Next, in the region 2, what is EA? Say this, suppose that you consider this EA is positive. That is sigma by 2 epsilon naught with positive sign. Why? Because this is a vector addition. This arrow is pointing in the same direction with the same magnitude. That's why here we are writing sigma by 2 epsilon. So what is the total? 2 sigma by 2 epsilon naught. That is sigma by epsilon naught. Sigma by epsilon naught. Okay. Right, here let us go for the region 3. This is equal to, what is EA? Let us take this to be a positive. Sigma by 2 epsilon naught. EB is pointing in this direction. That's why you have to put negative and its magnitude is sigma by 2 epsilon naught. plus this thing and minus same thing is equal to 0. So I will summarize the result here. E1 is equal to 0, you have here 0. E2 is equal to how much? Sigma by, instead of 2 epsilon naught, now you have sigma by epsilon naught. Here on this side you see all of those things here. E3, in the region 3 you have again 0. Okay, 0. So what is the electric field in this region 1? 0. What is the electric field in this region? That means in intermediate region. In the place between the two plates, you have non-zero electric field, that is sigma by epsilon only, not 2 epsilon. In the region 3 already you got 0. See here E3 is 0. That means you do not have any electric fields, okay, outside of this parallel plate arrangement. But inside these two plates, always you have a non-zero field which is given by the sigma by epsilon naught. So here we are using superposition principle, but I am discussing this in the applications of Gauss Law of electrostatics. Why? Because we already evaluated the field at infinite sheet of charge. Here we have two infinite sheets, of course, finite. Yeah. So for each and everything we already evaluated electric field as sigma by 2 epsilon naught. Now I am taking those already derived expressions and using them in the superposition principle. See here, this is what the importance of superposition principle also. Superposition principle here, for in case of superposition principle of electrostatic field, see, total electric field is equal to the vector sum of the individual electric fields. Okay, right. This is about the application of parallel plates. You see here in the diagram, electric field is uniform. This field is also uniform, not changing with the R. Even this sigma by epsilon naught, it is also uniform. Okay, it does not change very much, and the field lines are equally spaced. You see in the middle portion, but at the edges. So due to some edge effect, you have curved lines here. Field lines are not uniform, field is not uniform. That's why your evaluation, your total intensity applies here exactly. You cannot apply this here or here. That's why we imagine infinite plates, okay, in the applications of Gauss Law. Right. Next, let us go further. Next application, what is that? Yeah, it is very simple application, deriving the Coulomb's law from the Gauss law of electrostatics. We have already done this thing. Yeah, you see here, this is a point charge, field lines are coming out. Okay. Field lines are coming out from that. Yeah. Now, what is this? Derivation of Coulomb's law from Gauss law. Okay. Right. For that you are taking a positive charge. Okay. Here field lines emerge out from this charge. Okay. In order to get the Coulomb's law, what we are doing, we are considering a point charge of, consider a point charge with charge plus q coulombs. Okay, say this as plus q, say this as plus q. Now, in order to derive the Coulomb's law, let us just try to find the electric field at any point in the field of this point charge. For that, you have to take a Gaussian surface. Okay, you have to take a Gaussian surface. In this case, it is circle. Okay, right, circle, or if it is three-dimensional case, it is a sphere. Okay, encircling this charge. Okay, now you want to apply the Gauss law. Yeah, for that I am taking a point here. Suppose that you want to find electric field intensity at this point. Say this point as P. Yeah, let us consider some infinitesimal space. Okay, ds. The direction of it will be like this. What is this? What is this direction? This is the direction of field E. Okay. Right. If you take an infinitesimal area here, these two things will be parallel. Okay. Right. Now both of ds and E are pointing in the same direction. Okay. So the angle between these two things is 0. So now let us try to apply the Gauss law here for this spherical Gaussian surface. So according to the Gauss law, according to the E dot ds is equal to q by epsilon naught. How much charge is inside the Gaussian surface? Plus q. We need not to change anything here. Okay, now let us go for LHS. Okay, let's go for LHS. See, here I am expanding this EDS. So integral mod E mod ds. Okay, cos how much angle you are having with E and ds? If you take another field line here, the angle between these two things is 0. Cos 0, this is equal to q by epsilon naught. Okay. Now cos 0 is 1, so you just have integral E ds into 1. I am not writing that. This is equal to q by epsilon naught. So since E is constant over the Gaussian surface, you take E outside and just you write integral ds is equal to q by epsilon naught. What is integral ds? Total surface area of the Gaussian surface. So what is the radius of your Gaussian surface? Say this is r. Okay, this is r. This distance here to here. That means here to here. Okay, or yeah. Now, so your total area of the Gaussian surface is E into 4 pi. What r you have to write? Small r square. Okay, is equal to q by epsilon. Because this is a formula for the surface area of the sphere. Okay, right now. Okay, let us write the expression for E. You are having q here. On this side, you are having 4 pi r square, epsilon naught here. Okay. Otherwise, you write this 1 by 4 pi epsilon naught q by r square. What is this? It is Coulomb's law. Okay, almost Coulomb's law. Okay, this is a force. Why it is giving force only, even though it is heat. It gives you the force acting on the 1 Coulomb charge placed at point P. If you are placing Q0 charge at that point, then what will be the force acting there? Okay. Using therefore force acting on Q0 charge at P is F is equal to Q0 into, we have one formula relating F and We have one formula relating F and E. Okay, that is F is equal to Q naught E. We just got the E value. You just substitute that value. Then you get 1 by 4 pi epsilon naught Q. Again you are having Q naught. Q naught by R square. Therefore, what is the final formula you got? F is equal to 1 by 4 pi epsilon naught Q naught by R square. So what is this? This is exactly the Coulomb's law of electrostatics. This gives you the force acting between the Q charge and another charge Q naught, which are separated at some distance, arbitrary distance. Okay. If you are exactly placing that Q naught charge at P, then the radius of the Gaussian sphere will be the radius between these two charges. Okay, right. This is the Coulomb's law of electrostatics from the Gauss law of electrostatics. Okay. Yeah, let us stop with this right for today. Thank you.